Now, the thing is, and I've talked through all of this on the slide, so actually I've gone through it in sort of more detail on the slides, if you like, because on the slides I've actually treated it row by row, okay? Now, I'm just going to write out the number of different possible ways to get to each peg, okay? So if this is my peg, let me just quickly write it out. So 1, 2, 3, 4, 5, 6, da, 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 bop, 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 and then one more. Yeah, I think just about squeezed it in, okay? The number of different possible ways to get that peg, well, there's only one way, okay? There's only one way of getting to that peg, okay? Then if I think about the next row down, okay, now I have a choice, right? So I can either go left or I can go right, okay? So now there's only one way of getting here and one way of getting here, okay? Because I either go left or I go right. That make sense? Yep. Okay, and then if I think about the next row down, so here, here, or here, okay, there's still one way of getting here, I just go all lefts. One way of getting here, I go all rights, but there's now how many ways of getting there? 2. I can either go left and then right, or right then left. Is that okay? So it goes 1, 1, 1, 1, 2, 1, okay? The next one down, okay, I've done it on the screen so you can watch this, it goes 1, 3 ways of getting there, 3 ways of getting there, and 1 way of getting there, okay? If I think about the next row down, well, I've actually already done this one. It's going to be 1, 4, 6, 4, 1. Does anybody recognise these numbers which I'm drawing in red? Anybody recognise them? It's not the normal distribution yet. So these numbers here are something called Pascal's triangle. Now, Pascal's triangle is a really, really cool thing. I'm not going to go into too much detail now about what it is. If you're interested, by all means, go away and look it up. Effectively, the way it works is all the outside ones are 1, okay? And then to get to the next row, so to get to the next number, you add the elements which are diagonal to it. So, for example, to get this row here, you would add the elements which are immediately diagonal to it on the row above, okay? So 1 plus 1 would make 2, okay? To get this element here, you would add the diagonal elements above it, so 1 and 2, that makes your 3. So everyone see that? To get to your 6, you'd add those two together, so you get the 3 and 3 to get 6. So knowing that the outside ones are going to be 1, and you can see that from here, because there's only either all lefts or all rights to get to those elements, what element's going to go here? So on the next row down, what do we predict? What? 5?
10, 5.
Exactly, yeah? And if you wanted to do the next row down, you could go 1, 6, 15, 20, 6, 15, 6, and 1. Yeah? Now, look at this, okay? So for 6 choices, that's what I've got on the screen here. I've represented a perfect situation here. Represented a perfect situation, okay? So you know that there is only one way of getting into bin 0. There are 6 ways of getting to bin 1. Because you're thinking about the next row down, you're literally going 1, 6, 15, 20, 15, 6, and then 1, okay? Thinking about the next row down, and I've represented a perfect situation. In other words, if each ball were to take the one path, okay, so one unique path, so a ball can't take the same path. So for example, if a ball took left, 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 and then right, another ball can't take that exact same path in that order. So another ball could go left, right, left, right, left, 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 but it can't do this same path again. Does that make sense? So I'm basically saying each ball takes a perfect path. Once a path has been ruled out, another ball can't take that exact same path. It has to do a new path. Okay? Now, if that were to happen, I've represented that situation on the board. Okay? So each ball basically lands in the bin according to if it takes a perfect path. Okay? Do you recognize this shape? It's this bell shape, right? It's this bell shape, okay? So on the outside bins, in fact, you can probably see it here if I just draw over the top of it. On the outside bins, there is a low chance of ending up in those 2 bins because there's only one path each which gets you into that bin. So the chance of a ball taking all lefts or all rights is really low, okay? Whereas the paths in the middle, you now have combinations of lefts and rights, okay? So in actual fact, it's more likely that a ball will take an even number of lefts and rights. In other words, it's more likely that it's going to end up in that bin there. Does that make sense to everyone? Yeah? good, fantastic. So you're just thinking about this, okay, just thinking about this, thinking about the bell-shaped curve. Now, of course, this is still a binomial situation. This is still binomial because it's discrete. It can only end up in this bin, this bin, this bin, this bin, or this bin. Now, can I draw your attention to what's on the screen? So I've actually done the probability distribution here, and I've taught you how we calculate the probability distribution. Okay, it's literally just binomial. I've drawn the probability distribution on the screen. Okay, could you find me, given that the number of trials is 6 in this case, I've kind of done 2 extra rows on the screen. Could you find me the expectation and could you find me the variance? In other words, could you tell me which bin do you expect a ball to end up in? And also, what's the variance? So how many bins across are you varying by? Okay, what's the spread of your bins? Can you have a go at calculating that for me? Have we done it? So what do we think the expectation is? Bin 3, and you can see that in 2 ways. Number 1, it's the most likely bin. Yeah, it's the most number of paths which get to that bin. It's bin 3. Okay, but you can also treat it as simply just binomial formula. Okay, because the expectation of a binomial formula is just n times p, right? So 6 times 0.5, which of course is equal to 3. So in other words, you expect a ball to end in bin 3, and that makes sense. Okay, how do you calculate variance? Yeah, good. So it'd be 6 times 0.5 times the probability of failure, which is 0.5. Absolutely. So in other words, this is going to be 1.5. Yeah? Yeah, good, fantastic. Okay. Right, okay. So let's have a look at that. So have a look at the screen. Now 1.5, of course, this number is about 1.5. Okay. In actual fact, if we did this more regularly, and then we took the square root of it, for example, the standard deviation will actually come out as 1. Okay, the standard deviation should come out as 1. I've put about 1 for the variance because I guess it is about 1. It works out slightly better if it's actually 1 because it's a little bit easier to explain. Okay, but what this literally means is that you expect to land in bin 3. Okay, and that makes sense on the screen because you've got bin 3 here. Yeah, you've got bin 3 here. Let me get rid of that. This thing here means that the variance means that you are sort of 1 bin each side. So the expected deviation is 1 bin away from bin 3. Okay, so if you have a look at the screen, you expect to be in bin 3. That's the ball you expect to land in. And then effectively, you've got 1 bin deviation each side. So that's the standard deviation. Does that make sense? So in other words, if you expect to land in bin 3, the next bin that you expect to land in is either bin 2 or bin 4, 1 bin across. Okay? The next bin that you expect to land in after that, the next most likely bin is either bin 1 or bin 5, and then the next most likely one after that is bin 0 or bin 6.
So if the variance is 3,
yep,
then you expect the next will be 0 or
exactly.
6.
Exactly that.
Okay.
Yeah, or within that range. Within that range. Yeah. So in other words, because the standard deviation is about 1, now like I say, I've fiddled with the numbers a little bit, but because the standard deviation is about 1, you expect the next likely bin to be 1 bin across. And you can see that nice and easily from this shape or from the shape which I've drawn on the screen there. Is that okay? Yeah? Good. So there we go, I've just summed that up there. The most likely bin is bin 3, okay? Then the next most likely bins are kind of 1 standard deviation across.